Welcome to the deep dive. Today, we're getting into matrices. Now, maybe you remember something hazy from math class. Maybe you picture the Matrix movie effects.
Yeah.
But we're digging into the actual math, these rectangular grids of numbers.
Yeah.
The sources we looked at, they really lay out the fundamentals.
Exactly. Think of this as, well, a shortcut. We want to pull out the core ideas, what matrices are, how they're structured, the different kinds, and, the first steps in working with them.
Right.
The aim is to make it clear, make it stick, and give you a real sense of why they're useful.
Okay, let's get right to it then. What exactly is a matrix, fundamentally?
So, fundamentally, it's like the sources say. A rectangular arrangement of numbers, just a way to organize numerical info. You might see something really simple, like a single column, maybe begin matrix 5 and 3 in matrix, or a square grid, like begin matrix 5 and 3 in matrix, even wider, begin matrix 5 and 3 in 1 and 3 2.
Numbers lined up neatly, okay? And terminology plural is matrices, right? And each number inside is an element.
Spot on, elements. And to find your way around, we talk about rows. Those are the horizontal lines and columns, the vertical ones.
It's like a spreadsheet.
Exactly like a spreadsheet. Rows across, columns down.
Got it. So how do we describe the size, the dimensions? I saw the term order used.
Yeah, order is the key term. It tells you exactly how many rows and columns there are. And it's always given as number of rows first, then number of columns.
Rows first.
Always. So a matrix with rows and n columns, that has an order of 1 times n. We say by n.
Okay, by. So if we take an example like begin in matrix 2 and 1 and 5, 3 and 2 and 7 and matrix, what's the order there?
Okay, let's see. 2 horizontal rows, right? And 3 vertical columns.
Yeah.
So its order is $2 times 33, 2 by 350. You'll often see matrices labeled maybe like A times 3, or, V of 5 times 3 for a 5-row, 3-column matrix.
Right, the subscript tells you the size.
Okay.
Makes sense. Now, back to the elements. We know they're the numbers inside. Is there anything more to them?
Well, besides just being the entries, it's useful to know the total count, the total number of elements. It's simply rows times columns. So like a $4 times 60 in matrix always has $4 times 66, which is 24 elements, no matter what the numbers are.
Right. So for Gata matrix 2 and 4 and 3, 0 and 1 and 2 and matrix, that one's $2 times 33. So 6 elements. Easy.
Yep.
But the source mentioned something interesting. If you know you have, say, 6 elements, they could be arranged differently.
Exactly. And that's where order really matters. If you know you have 6 elements total, well, you could arrange them as a $1 times 6 matrix, just one long row.
Okay.
Or a $2 times 3, 3, like the example you just gave. Or flip it, a $3 times 2, 2, or even a $6 times 1, or just one tall column.
Right. The factors of 6, basically. $1 times 6, 2 times 3, 3 times 2, 6 times 1.
You got it. The factors tell you the possible shapes, the possible orders.
So same number of building blocks, different structures.
Right.
And not just for 6, right? If you had 8 elements.
Same idea. For 8 elements, you could have $1 times 88, $2 times $4 times 2 $2, or $8 times 1. And knowing this order is fundamental because, as we'll see later, the dimensions, the order dictates whether you can even do things like add or multiply matrices together.
Ah, right. Compatibility. Okay, that gives us a solid base. Now, the sources start classifying matrices, giving them different types, like meeting the different characters. Where should we start?
Let's start simple. First off, the row matrix. Name kind of gives it away, right?
Just one row.
Exactly. A matrix with only one single row, like a B dollar. That's a $1 times 2 2-row matrix. You'll also hear these called row vectors. That term pops up a lot in linear algebra, physics, graphics.
Okay, a horizontal line of numbers, row vector. Makes sense.
Yeah.
And the opposite must be?
A column matrix. You guessed it. Just one column. For instance, begin matrix, that's order $2 times 1 ohm.
Right.
And just like row matrices or row vectors, these are often called column vectors. Very important for representing things like points in space or maybe forces.
Row vector, column vector. Easy. Next one, square matrix. Sounds like its shape.
Precisely. A square matrix has the same number of rows as columns. Mel equals not. So begin matrix C and D and G. That's a $2 times 2 a 2 square matrix. Or begin matrix 5 and 7 and 4, 2 and 1 and 0 and 3 and 4 in matrix. That's $3 times 3 3 square. These are really important and they have special properties like determinants, inverses, stuff we need for solving equations.
Got it. Rows equal columns. So what if they don't match?
Then it's just a rectangular matrix. Simple as that. Number of rows is different from the number of columns. Like begin matrix 2 and 4 and another and 5 and matrix, that's $2 3 3. Or begin matrix 3 and 1 1 and 7 and matrix, that's $3 times 2 edo. They just look like rectangles, not squares.
Okay, row, column, square, rectangular. Build in the vocabulary. What else?
Then there's the zero matrix, also called the null matrix. And it's exactly what it sounds like.
Well, with zeros.
Every single element is zero. Could be a row, like $0, a column, like a begin matrix, a square, like begin matrix, zero, and a matrix any size. The key is all entries are zero. It acts a bit like the number zero does in regular addition, as we'll see.
The nothing matrix. In a way.
Yay.
Okay. How about the diagonal matrix? That sounds a bit more specific.
It is. A diagonal matrix has two conditions. First, it must be a square matrix.
Okay.
Second, all of its elements are zero, except potentially the ones on the main diagonal.
The main diagonal, that's top left to bottom right.
Exactly. Sometimes called the leading or principal diagonal. Everything off that diagonal has to be zero.
Can you show us one?
Sure. Begin matrix 0 and 3, end matrix. That's a $2 times 2, 2 diagonal matrix. See, the 2 and 3 are on the diagonal, the other spots are zero.
Right.
Or a bigger one. Begin matrix 5 and 0 and 3, end matrix 5 and 2 and 0, 3 end matrix. That's a $3 times 3, 3 diagonal matrix. These are nice because they simplify a lot of calculations later on.
Okay, I see it. Only the diagonal can have non-zero numbers. Everything else is zero. And the last type listed here is the unit or identity matrix. Sounds important.
Oh, it's crucial. The unit matrix, almost always written as a capital dollar, is a special kind of diagonal matrix. It's diagonal, so it's square, and everything off the diagonal is zero. But the extra condition is every element on the main diagonal must be exactly 1.
So for $2 times 2, 2, it would be begin matrix 1 in matrix.
Okay.
And for $3 times 3, 0, begin matrix 1 in matrix.
Exactly. That's the identity matrix. It acts like the number 1 does in multiplication. Multiply any matrix by $1 if the sizes work, and you just get the original matrix back.
The multiplicative identity.
It was super fundamental for solving equations, doing transformations. Lots of things.
All right, that's a good tour of the main matrix types. Now, the source material moves to an operation, the transpose of a matrix. What does that involve?
The transpose is pretty visual, actually. You take a matrix and you create a new one by swapping its rows and columns.
Swapping rows and columns.
Yeah. The first row becomes the first column, this one row becomes the second column, and so on. If your original matrix is Ellery, the transpose is written Ellier, or sometimes Ellery.
Okay, so rows turn into columns. Can we see an example?
Sure. Let's say I want a matrix 2 and 3 and 1 and matrix. What's the order of that one?
2 rows, 3 columns, $2 times 3, 3.
Right. So it's transpose 1 and T. We'll swap that. It'll be $3 times 2, 2. The first row 2, 3, 1 becomes the first column. The second row 4, 7 becomes the second column. So 1 and T is 3 and 4, 3 and 7 in matrix.
I see it. It's like you flipped it along that main diagonal line almost. Okay. Next topic. Equality of matrices. When can we say two matrices are actually the same?
Two things have to be true. First, they absolutely must have the same order. Same number of rows, same number of columns.
Same shape, basically.
Exactly. Second, every single element in one matrix must be equal to the element in the corresponding position in the other matrix.
So same size, and all the numbers match up in the same spots. It seems logical. The source even used this to solve for variables.
Yeah, that's a neat application. If you know two matrices are equal, but one has unknown variables, you can set up equations. Like their example, orbitals 2 and y, a2 and b, plus 1 and 3, 1 and 5 and matrix. Since they're equal, the top left elements must match. $6, $2 equals dollars. The top right, dollars, $3. Bottom left, bottom right, bottom right, bottom right. Bottom plus 1 equals 5y.
And then you just solve those simple equations.
Yeah.
$6, $2, 2, $6, B, 4 R's. Clever.
It falls right out of the definition of equality.
Right. Okay, let's move on to combining matrices, starting with addition. Are there rules? Can we just add any two matrices?
Nope. There's a key rule, the most important one for addition. The matrices must have the same order. You can only add a $2 times 3, 3 to another $2 times 3, 3. You can't add a $2 times 3, 3 to a $3 times 2, 2.
Compatibility again. Same dimensions required. Okay, assuming they do have the same order, how does the addition work?
It's very straightforward. You just add the elements that are in the same corresponding element.
Element by element.
Exactly. So if you have A begin matrix 2 and 1, 5 and 6 are in 4 matrix, they're both $2 times 2 and 2, so we can add them. ABL plus B would be. Top left is $2 plus 3, $5. Top right is $1 plus 2, 3, 3. Bottom left is $5 plus 167. Bottom right is $6 plus 4, $10. So all plus B begin matrix 5 and 3 eccentrics.
Simple enough. Add the matching spots. The source mentioned properties too, like the commutative property. What's that mean here?
Commutative just means order doesn't matter. For addition, all plus B gives the exact same result as baller plus A.
Like $3 plus 5, 5 is the same as $5 plus 3, 3.
Precisely. Matrix addition is commutative.
Good to know. And the associative property.
Associative deals with grouping when you add 3 or more. It means A plus B plus CAD is the same as A plus B plus C.
So it doesn't matter if you add the first two, then the third, or the last two, then the first.
Correct. The grouping doesn't change the sum.
Okay, commutative and associative. That's helpful. And the result of adding two matrices, what's its order?
It keeps the same order as the matrices you added. If you add 2 molar times n matrices, the result is also dollar times NA.
Right. And this leads to solving equations too, like if we have 1 ball plus xb double, where x is an unknown matrix.
Yeah, you can solve for $6. Just like regular algebra, you'd subtract a from both sides. Scalar are pretty similar to subtraction.
Subtraction of matrices. I'm guessing the rules are pretty similar to addition.
Exactly the same compatibility rule. You can only subtract matrices if they have the identical order.
Same dimensions needed. And the process.
Also, element-wise. Subtract the corresponding element of the second matrix from the first.
Can we do a quick example?
Sure. Let's say A begin matrix 5 and 1, 4 and 2 in matrix, both $2 times 2 and 1.
Okay.
A B all would be top left 5 3 is 82 2, top right 4 is $4, bottom left 244 2 tas, bottom right $1 2 and 1 4 and 2 and 1 Waller. So A B begin matrix 2 and a 1 in matrix.
Got it. Element by element again, just subtraction this time. Now, we mentioned the zero matrix earlier. You said it acts like zero in addition.
Yeah.
The additive identity.
Yes, exactly. The zero matrix, or null matrix, is the additive identity for matrices. Adding the zero matrix of the correct size, of course, to any matrix ABLer doesn't change dollars.
So all plus dollar is A2.
And $0 plus A. The order doesn't matter there either. Like begin matrix 4 and 7 0 0 0 n matrix just gives you begin matrix 4 and 7 n matrix back again.
Makes perfect sense. The nothing element for addition. And if there's an identity, there's usually an inverse. Additive inverse.
You're thinking exactly right. The additive inverse of a matrix dollars is another matrix, let's call it dollars, such that when you add them, A plus B, you get the zero matrix.
So they cancel each other out to zero.
Precisely. 1 plus B and baller plus A is just dollars. And it turns out the additive inverse of D is just a lero. You get it by negating every single element in all dollars.
Oh, okay. So if A big matrix 4 and 3 and 7 in matrix, then dollars is just begin matrix 4 and 3 and 7 matrix.
Exactly. And if you add a nodal element by element, you'll see everything goes to zero, giving you begin matrix 0 0 in matrix.
Right. And this is key for solving those equations like Zolitzer's BATA, because BA is really a baller plus.
That's the formal way to think about it, yes. You're adding the additive inverse. The source shows examples solving for x in equations like dollar plus xBA and also sexBA using these principles.
Yeah, it's nice how it mirrors basic algebra concepts. Additive identity, additive inverse. It carries over.
It does. For addition and subtraction, the parallels are very strong.
Okay, add, subtract, check.
Yeah.
Now, multiplication. The source starts with something called multiplication of a matrix by a scalar. What's a scalar?
A scalar in this context is just a plain old number, a single value, not a matrix itself.
Okay.
So scalar multiplication means multiplying an entire matrix by one of these single numbers.
And how does that work?
It's probably the simplest operation. You just multiply every single element inside the matrix by that scalar number.
Ah, okay. So if I have, say, the matrix begin matrix 4 and a 1 matrix and the scalar is 3, I just do $3 on 4 or 3 and $3 times 1.
Yep. Resulting in $12.33. The source has other examples, like $2 begin matrix, this 4 and 2 in matrix becomes begin matrix 2 in matrix. Or even with fractions, fraction of matrix only becomes begin matrix 3 and 2 in matrix.
Distribute the scalar to every element. Got it. The source even combined this with addition subtraction, like finding $0 plus 2b3CAR.
Right, and you'd follow the standard order of operations. Do the scalar multiplications, first find $2b and $3.
Then do the addition and subtraction.
Exactly. And scalar multiplication is also used in solving equations. If you had, say, 1 plus 2x zeros, you'd isolate 2x3's first, 2x burs BAO, and then you'd multiply by the scalar for our quantity to find $6.
Okay, scalar multiplication seems pretty intuitive. Now, the big one. Multiplication of matrices. Multiplying one matrix by another. I hear this is trickier.
It is definitely less intuitive than addition or scalar multiplication. There's a crucial rule first. Compatibility for multiplication.
Okay, what's the rule?
For you to be able to multiply two matrices, let's say other times dot, in that order, 8 roll, the number of columns in the first matrix must be exactly equal to the number of rows in the second matrix.
Columns of the first must match rows of the second? Okay.
Let's say a $0 is dollars and $0 times lens, and a $0 and n columns. And dollars is T times Q, P rows, Q columns. The product A molar is only possible if non equals P dollar.
The inner dimensions must match.
Exactly. Molars times underline times Q, the not and dollars must be the same.
And if they do match, what's the size of the resulting matrix?
The result takes the outer dimensions. It will be an Euler times Q matrix. the number of rows from the first matrix, and the number of columns from the second.
Okay, inner dimensions match to allow it. Outer dimensions give the result size. The source uses 1 matrix, 3 and 4, 5 and n matrix in a not dot. Let's check.
Okay, A is $2 times 22. B is also $2 times 22.
So columns of A is 2, rows of B is 2. They match.
They do. So ABR is possible, and the result outer dimensions are $2 and $. So the product ABR will also be a $2 times 2B matrix.
Right, okay, compatibility checked.
Yeah.
Now, how do we actually do the multiplication? The source says something about multiplying rows of the first by columns of the second.
That's the core idea. It's not element by element like addition. It's a row by column operation.
Row by column.
Yeah. Let's start with that example. ABAB begin matrix 3 and 4 at once day. To find the element that goes in the first row, first column of the answer matrix.
Left spot.
Right. You take the first row of A, which is 3, 4, and you take the first column of B, which is begin matrix 1, 3, and matrix.
Okay. Row 1 of A, column 1 of B.
Now you multiply corresponding elements and add them up. It's like a dot product.
Yeah.
So it's first element of row times first element of column plus second element of row times second element of column. In this case, $3 times 1 plus 4 times $3.
Which is $3 plus 12 equals 15.5. So 15 is the element in the first row, first column of the product ABBN.
Exactly. That's the fundamental step. You repeat that process, matching rows from the first matrix with columns from the second to find each element of the resulting matrix.
Okay, I see the start of it. It's definitely more involved. A combination of multiplying and adding, and you have to track which row hits which column. Seems like we'd need to walk through the rest of the positions to really get it down.
Absolutely. Matrix multiplication is probably the most complex of the basic operations, but it's incredibly powerful. It's used everywhere. From 3D graphics rotations to solving big systems of equations, it definitely warrants a closer look at the whole process.
Agreed. But wow, we've actually covered a lot of ground already. We've got the basic definition. Matrices as rectangular arrays. We understand order and elements. We've met the main types. Row, column, square, rectangular, zero, diagonal, and that all-important identity matrix, dollars.
Yep, the whole cast.
Then we looked at the transpose flipping rows and columns. We saw when matrices are equal same size, matching elements.
The crucial rules.
And we covered the operations. Addition and subtraction, element-wise, need same order, and multiplication by a scalar. Just distribute the number.
Right.
And we've just dipped our toes into matrix multiplication, learning the vital compatibility rule. Columns of first must match rows of second.
That's a solid foundation. Grasping these basics really is the key to unlocking everything else in matrix algebra. It sets you up for the more advanced stuff and seeing where it all gets applied.
So the big takeaway feels like
Yeah.
these aren't just random grids of numbers. They're a structured language, a way to handle information, with consistent rules for how they interact.
Well put. And it's amazing how these relatively simple structures underpin so much complex modeling and problem solving across science and technology.
Which leads perfectly into our final thought for you, the listener. Consider this. How can these ordered arrays, these matrices, represent really complex things? Think about computer graphics. Rotating an object on screen is matrix multiplication. Or physics, describing systems with multiple interacting parts. Or, hugely relevant today, data science, organizing massive data sets for analysis.
The applications are vast.
So the question to ponder is, where else might matrices be working behind the scenes, in places you wouldn't expect? What other complex systems could be modeled or understood using these tools? We encourage you to keep an eye out for them. Thanks for joining us on this deep dive into the fundamentals of matrices.